I request Dr. Burkholder to give a session engineer.
May I begin?
Yeah, can we start? Professor Bruce
Thank
Watson.
you. Thank you. I'm Bruce Watson from South Africa, University of the Witwatersrand in Johannesburg. And I would like to thank the organizers of BRICS for inviting me to give this talk.
Yeah.
My talk is on the boundary between functional analysis and probability and measure theory, that sort of boundary area. And I'll be talking today about discrete time martingales, mixingales, mixing processes in the setting of Riesz spaces, or if you prefer, vector lattices. And this was joint work, most with Wen-Chi Kuo, Kunrad Labuskachny, David Rodder, Michael Rogans, and various other collaborators over the years, and has in part been funded by our National Research Foundation. I'm going to start quite simply with talking about expectations. If we start with a probability space, omega f mu, omega here is a set, f is a sigma algebra of subsets of omega, and mu is a positive measure where the measure of omega is 1. We're talking about the measure theoretic setting, and a random variable in this context is an L1 function over the measure space omega f mu. And as many of the audience may probably knows, the expectation of f is merely the integral of f over omega with respect to mu. Here, f cannot just be classed as a map from L1 through to the reals, but it can also be classed as a map from the L1 space to another L1 space over omega with respect to the trivial sigma algebra of almost everywhere constant functions. And if we take the G here as being the set of measurable sets of measure 0 or measure 1, then E becomes a map into L1 omega G mu, which is again a subspace of the L1 space omega f mu. And the reason why it's instructive to look at it like this is that leads us into the concept of conditional expectation. Now, if we take sigma, capital sigma, as a subsigma algebra of f, the conditional expectation of the random variable f with respect to capital sigma, which we denote by EF sigma, is capital F, where f is sigma measurable, and for each set A, which is sigma measurable, the integral over A of capital F with respect to mu is equal to the integral over A of our original little f with respect to mu. The existence of the conditional expectation of each f in L1 omega f mu follows from the Radon-Nikodym theorem. And here we observe that the conditional expectation map is a map from L1 omega f mu to L1 omega sigma mu, where sigma is the sigma algebra of f, and that is a subspace of L1 omega f mu. And further, the conditional expectation map is order continuous. It's a positive map. It maps non-negative functions into non-negative functions. And further is a projection, and it maps onto the space L1 omega sigma mu. And it also has one extra property, that the almost everywhere constant functions are mapped to the almost everywhere constant functions. Now, where does this take us? Now, we're going to abstract this to the Riesz space or vector lattice setting. So a vector lattice is a vector space with an order structure, where the order structure is compatible with the vector space structure, and the supremum of any two elements in the space exists. And that gives you what's called a Riesz space. Now, if we have E as an Archimedean Riesz space, that is a Riesz space where the limiting properties exist in some well-behaved way. With a weak order unit, I'll talk about that. We call a positive order continuous projection T on the space with range R of T, a Dedekind complete Riesz subspace of E. We call that a conditional expectation operator on E if it maps weak order units to weak order units in E. Now, a weak order unit is an object in our space which has to be non-negative. And if we take the infimum of n times E with our F, which is non-negative in the space, we take that infimum and we take the supremum over n of that, it has to give us back our element. So if we think of classical L1, we can come back here and let's see what we get. In classical L1, if we take E, our space to be L1 omega F mu, where omega F mu is a probability space, and we take sigma as a sub-sigma algebra of F. Firstly, we note that E is a Dedekind complete Riesz space. The constant 1 function, or the equivalence class of that, the AE equivalence class of the constant 1 function, is a weak order unit. And the map TF, which maps F to its conditional expectation, is a Riesz space conditional expectation operator. So that shows us that certainly in the special case of classical theory, the Riesz space definition coincides with what we would hope for. And the converse is also true. If we take a Riesz space conditional expectation operator in L1, where that's L1 over omega F mu, and mu is a probability measure, then we know that there exists a sub-sigma algebra, sigma of F, which generates that conditional expectation operator. And that's due to a famous paper by Douglas on contractive projections on L1 spaces. Now, for our consideration here, we can also assume that we are looking at strictly positive conditional expectation operators. In other words, if the conditional expectation operator is acting on a non-negative random variable or equivalence class of them, then the only way that that conditional expectation can be 0 is if that is a 0 equivalence class. If that's not the case, we can always form a quotient space in the vector lattice setting. Now, as it happens, when you want to work with conditional expectation operators, either in the Riesz space or the classical setting, as we'll see, we can extend the domain of the conditional expectation operator to its maximal domain, the largest domain where that remains as a conditional expectation operator. So let's work in the Riesz space setting first, and then I will look back at the measure setting. So we take a Dedekind complete Riesz space with weak order unit and a strictly positive conditional expectation operator T on that space. And we are going to construct firstly the extension of that space. And we do that by looking at what's called the positive cone of the new space. We call that DOM T. That's going to be the non-negative elements in our space. And those are all the elements F in the positive cone of the lateral completion, in fact, the universal completion of that space, so that there exists a net which is upward directed with supremum equal to our element F in the universal completion. And the original net F alpha comes from the non-negative elements from our original space E. And we further require that the conditional expectation operator acting on F alpha gives a bounded family or bounded net in the universal completion. So we take the set of those element F as indicated here in the second point from the positive cone of the universal completion, and we take the difference of those elements to form a Riesz space out of it. Remember, Riesz spaces are very much like measure spaces. If you have an element of a Riesz space, you can always decompose it into its positive part and its negative part. Now we're doing the opposite operation. We are reconstructing the elements of our Riesz space as the difference of two non-negative vectors. Now, E hat here, it can be shown to be Dedekind complete and a Riesz space. And one can also show that the original Riesz space E is order dense in this space. And the weak order units in our original space E are again weak order units in E hat. And for reasons which we will see just now, we denote the space E hat as L1T. It's an L1 type of space generated by the conditional expectation operator T. And in fact, if you restrict yourself to the case of E being classical L1, omega F mu, and T being your expectation operator, the space L1T is exactly your L1 space. So while you might have, if we took our original Riesz space, let's say as L infinity over omega F mu, E hat would still be L1 over omega F mu. It gives us the extension, the maximal extension. Now, if we've extended the space, we need to extend the operator, because our claim is that this is the maximal domain for our conditional expectation operator. So now we build the extension of the operator. So we take F in E hat plus, in other words, in dom P. We know that we can form a net F alpha from the positive cone of E, which has a supremum as its supremum F, and that it has T of F alpha bounded in the universal completion of E, that's EU. And so since TF alpha is bounded and EU is Dedekind complete, this net has a supremum. We take this upwards directed and we take its supremum and we label that supremum T hat of F. And that's an element in E hat. That can be shown. And we extend T hat to the whole of the space by applying T hat to the positive part of F minus T hat applied to the negative part of F. And that defines T hat as a conditional expectation operator, believe it or not, on E hat. And it can be shown that this is the maximal extension which is possible. The essential ideas of this extension can be found in a paper from 2002 by Hölder and de Pachter. And we're going to look just now, after some other properties, at what these mean for L1. But let's continue here. We now look at some of the averaging properties of conditional expectation operators, and we start by looking carefully at the measure theoretic case. If we have sigma as a sub-sigma algebra of F, and we look at the conditioning with respect to capital sigma of f, little f in L1, then we recall that the requirement was, we look back here, that the integral, I just need to keep track of my slides here. Here we go. The integral over capital F of A is equal to the integral over little f of A for all A in this sub-sigma algebra. Well, now if we take a characteristic function chi A, where A comes from the sub-sigma algebra, and we take B in the sub-sigma algebra sigma as well, the integral over B of the characteristic function of A times the conditional expectation of f with respect to sigma is exactly the integral over A intersection B of the conditional expectation of f with respect to sigma. Now, since A intersection B is in the sub-sigma algebra sigma, we can use the properties of conditional expectation operators to say that that is just exactly the integral of f over A intersection B, which is again the integral over B of the characteristic function of A times f d mu. And that's for each A and B in sigma. So we have, due to the uniqueness of the conditional expectation, that the conditional expectation of the characteristic function of A with respect to sigma is exactly the characteristic function of A times the conditional expectation of f with respect to sigma, as seen here. Now, what can we do in the vector lattice setting? For this, if we have a band, or if we, when this band is generated by some element G in the range of T, and we can take a band projection PG onto this band generated by G, then we have an analogous property here that the operators T and the band projection PG commute with each other. This is a fairly abstract form of this, but we will get a more concrete form in a few moments. But first, let's look at some of the spaces. We introduced the space L1T a few slides back. Now we can introduce a space L infinity T, where we take all the elements in L1T, which are absolutely bounded by some G from the range of T, the positive cone of the range of T. And now, using functional calculus, if one wants to, one can form powers in these Riesz spaces. So one can actually extend an LP type operation. The most obvious one of these is when P equals 2, and it's one of the most useful. So you can define an L2 space as well. So that's all the functions, all the elements on the L1T of L1T whose squares live in L2 in L1T. And we'll talk a little bit more about how the functional calculus is defined here. Well, if we have, so if our space is L1T, we call it T universally complete. So in the case we're looking at E equal to L1T, we have some very special properties. That the range of T is universally complete and is in fact an algebra. So it's a ring. You can multiply elements within it and stay within it. Further, if you take anything in the range of T that is a weak order unit in our space, then it's actually invertible. It's an invertible element of our space. Also, the LP spaces, these abstract LP spaces, are all RT modules. So you can multiply vectors in these LPT spaces by elements from the range of T and end up back in LPT. And all of these properties are consequences of averaging. And further, L infinity T is also an F algebra. And one can actually show that all of the LP spaces are also L infinity modules. And now we can write out our averaging property for the L1 T space rather nicely. So in this case here, T is an averaging operator in the sense that if we take F in the range of T and G in our L1 T space, then the product FG is again back in our L1 T space that's defined, and T applied to that is F times T of G. So this brings back many of the averaging properties one expects. And further, one can define vector-valued norms on these spaces. The norm now takes its values in the range of T, and it's strictly positive. We require that it's strictly positive. In other words, the only element of the space who has a vector norm equal to 0 is the 0 vector. It is homogeneous with respect, positively homogeneous with respect to elements from the range of T. So in other words, phi of GF is equal to the absolute value of G times phi of F for F in E and G in the range of T. And lastly, there's a triangle inequality. Those are the defining properties, and we have a collection of these. The map on L1 that maps F to TF, T mod F, defines an RT valued norm on L1. And we can do this for the other LP spaces as well, abstract LP spaces. They have vector norms, as shown here. Well, Krobler and Zuzi and Tribalesi showed that one could extend the Hölder inequalities to these spaces, as shown here. And if one extends these, one can then apply this to direct sums of copies of L1T to form a summation version of Hölder's inequality. Further, these LP spaces form a scale. So we have that LQ is contained in LP if Q is larger than P. And we also have that the vector norm of G with respect to P is less than or equal to the vector norm with respect to Q. Now we can apply these to sigma finite processes. In the 1980s, Gershaki and Mayer considered what they called sigma finite processes in the context of martingale theory. Here, we take a measure space, omega A mu, and a sigma finite, which is a sigma finite measure space. And for this to be interesting, we require that mu of omega be infinity. And we have that omega I is a partition of omega into mu measurable sets, disjoint mu measurable sets, each of positive measure. We take A0 to be the subsigma algebra of A generated by these omega I's. And we now let E, our Riesz space, be L infinity omega A mu, and take as our conditional expectation operator T as conditioning with respect to A0. Here we can directly compute the conditional expectation of F for each F in E, and for omega in omega I, that is equal to the mean of F over omega I, in other words, the integral of F over omega I with respect to mu over the measure of omega I. And the universal completion of the space is the equivalence classes of AE measurable functions. The L1 space, L1T, is the space of equivalence classes of mu measurable functions, so that the integrals of their absolute values are finite over each of the omega i's. In other words, we require f to be an a measurable function so that when it is multiplied by the characteristic function of omega I, that is in L1 omega A mu. T can be extended to a conditional expectation operator on this L1T, as can directly be seen here because these integrals are well defined on this L1T. The one function is invariant under T. Now we should note that the one function was in E because we took that as L infinity, but it is not in classical L1 omega mu. However, it is in L1T, and it is in fact a weak order unit for it. And the range of this generalized conditional expectation operator T, it consists of the equivalence classes of mu measurable functions that are almost everywhere constant on each of the omega i's. And this forms an F algebra, which is easily seen. The last of the spaces, L infinity T, consists of functions which are essentially bounded on each of the omega i's. The vector norms, the most important one is the T1 norm of f, which at omega I is equal to the integral over omega I of mod f divided by mu of omega I for omega in omega I. So again, this is again a vector in our space. And it should be noted here that classical L1 is contained in, but not equal to L1T. Classical L infinity is contained in the Riesz space L infinity T, but is not equal to it. But we do have the nice containment that L infinity T is contained in L1T, while in the classical case, we do not have that L1 omega A mu is contained in L1 omega. L infinity omega A mu is not contained in L1 omega A mu. So here we can also generalize Jensen's inequality, or Jensen's inequality. This was done by Grobler. And that says that if we have a convex function on R and f in L1T, then the conditional expectation of G of T is greater than or equal to G of the conditional expectation of T. And here I want to just show a little bit about how the functional calculus works in our vector lattice. So if we have disjoint components, so these are, if you can think of these as very similar to characteristic functions in the L1, in the measure space setting, we take components of our weak order unit. So if we were working in the measure space, we could take characteristic functions. And how do we act on G? If we have a summation of disjoint components scaled by alpha i's, G acts on the scaling components. And we can extend this action by order limit and Freudenthal's theorem to L1. We can also extend Clarkson's inequality. And I'm not going to go through the proof of that because I think time is quite short. And that uses our extension, it uses both Jensen's inequality and the extended Hölder's inequality.
Just a second, Bruce.
And
hello, Bruce. Yes, you have actually 4 minutes left.
should I finish up?
Yes, please.
We can do Burkholder's inequality, and we can do the Hajek-Renyi maximal inequality. And from that, we obtain strong laws of large numbers for martingale difference sequences, sub-martingale convergence theorems. And if we extend the concept of uniform integrability, we can talk about mixing processes and mixingales to get weak laws of large numbers for them. Thank you. Are there any questions?
Thank you very much. So if there is any question, we can ask now. So no question. Anyone from online participation? So there is no question even in the chat.
This can be extended to ergodicity, all manner of mixing processes, and there are some quite hard mathematical problems involved here, especially when you get to tensor product spaces.
So thank you for the nice talk. And
thank you.
We end the session here. Thank you.
Thank you.
Now we have the next talk, which will start in a couple of minutes.